Hello again, everybody. Welcome back. Today we're going to talk about thermal energy and temperature. This is the first part of a two-part series, so strap in and let's get rolling. This is a photo of a horse. What is this strange image called? Why does it look like this? Well, this is called a thermal image, sometimes called an infrared image. And why does it look like this? Well, the camera senses differences in temperature or infrared light, so it is actually able to see in a different light spectrum than we do. We see in what's called the visible light spectrum, and this camera can sense infrared light. Well, I was about to say pretty cool, but it's pretty hot. How can thermal imaging cameras be used? Well, let's take a look at this photo. What do you think this could be useful for? Taking a picture of a house like this. Well, this would be good for testing homes for energy leaks. So let's say you want to see if your house is being very efficient. You have to pay for your heat in your home, so you don't want it to be wasted. You don't want it to leave the house and try to heat up your backyard or your neighborhood. So you take a look at this and you can see areas where heat is definitely escaping, like these big, huge windows here. And so maybe you might want to look into a more modern window, a more efficient window that has better insulation. Other areas in the house absorb heat pretty well. Now this looks like it might be a window, but it's actually not. That's a solar panel, so that's why that shows up dark. There's no thermal energy escaping from that. That insulates the roof of the house very, very well. What do you think about this one? How could a infrared photo of a person be used like this? Well, it could be used for medical use. Possibly you can spot some health issues by looking at the temperature of a person's body. Like, for example, airports can use scanners to spot people coming in from other countries who might be sick. Maybe they could even have Ebola or SARS. In this diagram, you could see that maybe early stage diabetes can be spotted with extra thermal energy emitting from people's hands. So, interesting thoughts. In this clip, you'll see that the brighter colors, the red, the yellow, that indicates more heat, and the darker colors, the green, the blue, the black, indicates less heat energy being given off, less infrared heat. Photo like this, how could this be used? What do you see in the picture? I think it looks like an opossum to me, or actually two opossums, and these photos can be used for pest control. You can spot these animals that you don't really want in your house in the dark. You can maybe spot bugs in the dark, like maybe dark crevices in your wall, things like that. How about this one? What do you think this is? Well, this is for electrical maintenance. You possibly can spot wires overheating or getting ready to break. What do we have going on here? Well, this are plumbing pipes. So water pipes could be hot water. Plumbing maintenance, you can spot leaks, especially in hard to find and hard to access locations, like maybe behind walls. Now here's two photos of the same location. We have night vision and we have that infrared thermal vision. So how could photos like this be used? Well, maybe police departments or military could use this to try to find the bad guy hiding in the bushes here. Here he is right here. He does blend in pretty well, even with night vision, yet his thermal signature stands out very, very easily. He's definitely much warmer than the surrounding bushes around him. Here's a famous photo for the police used. This is the state of Massachusetts. This is a photo from what was called the Boston Marathon bomber. And there were two brothers, and one of them was hiding in somebody's boat just in their backyard, and the police were able to spot him, so you could see how brightly his body glows even though he's inside this boat. So the heat from his body is actually able to be seen through the boat. That's pretty cool. Okay, how about this photo? Well, in this photo, there is a runaway llama that these police officers are trying to chase down. Here's our friend the llama. And they were able to track him down and capture him safely, bring him back home. Kind of goes along with similarities here. What do you think's going on here? Well, in this case, fire and rescue is looking for an injured person that's lost in the woods. Here you can see the rescuers, the searchers, and the rescue dog. And here's the injured victim here who still is alive and still giving off heat. And the rescuers were able to find him in time and get him the help he needed. Here's a clip.
Out on a call, in the heat of the moment, a thermal imaging camera is indispensable. A vital tool that helps you quickly visualize your plan of attack, find hotspots, and save lives. Every engine and truck company should have at least one high-performance TIC on hand.
Now let's just kind of think. Let's brainstorm a little bit. What are some terms that you can think of when you think of the word heat? What about this one? Is there a difference between heat, temperature, and thermal energy? Well, we're going to find out later in this unit of study. First, let's review a few key terms that we would already know and would definitely be helpful for this lesson. Energy is the ability to do work or the ability to cause a change. And think about what are some forms of energy that you can think of. Maybe gravitational potential energy, maybe electrical energy, maybe chemical energy, elastic energy, many different types. Okay, what were the two main grouping of energy that we learned about in class? Well, the first one was kinetic energy. What is kinetic energy? Well, kinetic energy is the energy of motion. What are the two variables that go along with kinetic energy? That's right, speed and mass. And what's the other of the two main forms of energy, the two general forms of energy? Well, we got kinetic and we have, that's right, potential energy. Potential energy is defined as stored energy. And that stored energy is a factor of, let's say it's gravitational potential energy. That's a factor of height and the mass for gravitational potential energy. You may have learned in elementary school that all matter is made up of tiny particles. These little tiny particles are called, does anybody know? That's right, they're called atoms. And these particles, they're always in motion. So here you see these particles moving around. Some are moving a little bit faster than others, but they're all bouncing around, kind of doing their thing. The faster the particles in matter are moving, the greater their kinetic energy. And that should make sense because, as we recall, kinetic energy is mass and also a factor of velocity or speed. Now, which diagram shows particles at highest kinetic energy here? Yeah, you're right. This one does. This one has the fastest moving particles. These are moving pretty fast over here. Every once in a while you see one really zipping by. These are moving kind of fast. They're not moving very far though. And these ones are just kind of shimmying in place. All right, now let's take a look at a term you might not be familiar with. It's what is thermal energy? Thermal energy is defined as the total energy of all of the particles in a sample. Which diagram shows particles with the greatest thermal energy? So which of these diagrams has the most total energy of all the particles in a sample? Yeah, it's the same one. Yes, it's the same one because they have about the same number of particles. And the ones here are moving farthest and fastest on average. Now here's an interesting question. Which of these two things do you believe would have more thermal energy? This lit match or this snow fort? Interesting question. You're going to have to stay tuned for the answer, though. I'm not going to give it to you right now. Thermal energy, you'll find, depends on two things. First, the more particles there are, the more thermal energy the substance is going to have. A good way to picture thermal energy would be particles, kind of like, I don't know if you've ever seen the lotto drawing, where they have the balls in the chamber here. You see how they're all moving around. Some of them are moving around at a little different speeds than others, but they're all pretty active. The faster they're moving and the more of these balls, the greater the thermal energy would be. Now, if you could imagine just one ball in here, it might be able to bounce around a little bit more, but it's not going to be nearly as noisy. There's not going to be nearly as much motion going on. It's going to be less thermal energy. The second factor would be more particle speed, so how fast the particles are moving. The faster the particles are moving, the more thermal energy it's going to have. Here's a clip.
What I have here is a bimetallic strip with one type of metal on one side. It looks to be brass or bronze, and another type of metal on the other side. These two pieces of metal are attached, adhered to each other. When you heat the strip, given the fact that the two metals will have different thermal expansion coefficients, one will expand more than the other, and it will curve, the strip will curve. So I'm heating on both sides to convince you that I'm not cheating by just heating one side and having it expand. So that is a bimetallic strip.
What that man just showed you, it can be a pretty useful characteristic of metal, that metals do heat up, and when they do heat up, they can actually expand, get a little bit bigger in sizes. And that can be used for, say, a thermostat in your home. So a thermostat is like where you set the temperature at 72 degrees, and the furnace won't turn on until the temperature in the house gets below 72 degrees. So if it goes to 71 or 70 degrees, the furnace will turn on until it gets up past 72 degrees, and then it'll shut off again, and then that process continues. Another use of that would be for thermometers. You may have seen one of these, an outdoor thermometer like by your pool. So the metal, there's a metal in the thermometer that will expand or contract dependent on the temperature. Pretty cool. Here's a clip.
Do you know what happens with the length of something when you heat it?
Well, it gets longer.
It's a metal, at least, something that doesn't burn. In other words, metal, when you heat it, would get longer. And
Okay.
when you cool it off?
It'll get shorter.
It'll shrink. Have you ever actually proved it?
No, I haven't.
Well, that's what you and I are going to do. See, here's a block of wood, and on top of it, thumbtacks. And there's a sort of thick wire made of metal that goes all the way over to here, and it's resting on top of a needle.
Okay.
And you can see what the pointer is made out of. Okay, of a straw.
It's a straw, yeah.
So move this block back and forth. Move it that way, just slowly. And you see what happens to the needle?
Oh, it rotates and it rotates the straw at the same time.
Now see if you can get it so it's horizontal. Now here are 4 candles, which we'll light, and then put under the bar. What should happen to it?
Well, the bar will expand.
Yeah.
It'll get longer.
Okay. And what will happen to the straw?
It'll rotate.
Okay,
Because
let's
it's
try
moving
it.
forward.
You take 2 and I'll take 2.
All right. There's 1, 2.
Okay. Now slowly move the candles under the wire. Wait a minute, let me get this exactly horizontal first.
Okay.
There, okay.
Now it should start to rotate.
Is it moving?
Yeah, it's moving. It's going clockwise.
Yeah. Yeah, that's way down from that horizontal already, yes. Now that movement isn't very much, is it? Because we're magnifying it. As this rolls across the needle, it's rolling it, and we're using a pointer. So the expansion isn't great,
Yeah.
but it's amazing how much energy there is when you heat the molecules up. You're forcing them to move faster, and that's what makes something longer.
Okay, so when the molecules are moving faster, it's expanding.
Right. Okay. What should happen to the straw now?
It should go back.
Keep an eye. I'll blow out the candle. Watch the straw.
It's going back to
Yeah,
horizontal.
it's going back to where it was. Now, the movement of the molecules has a tremendous amount of energy, and we're going to put it to work in a sort of dangerous experiment, so I want you to follow my instructions very carefully.
All right.
First of all, safety glasses,
All right.
okay? Then, take a look at, here's a bar, has a hole in the end, and see this piece of metal? Take it out
All right.
and break it.
Oh, I don't think it
Tough,
can
right?
be done, yeah.
Okay, slip it back in the hole.
All right.
Through there, like that. Okay. Now, I'll tighten it up here as tight as I can get it. Okay. Now, I'm going to give you a blowtorch, and I'll take a blowtorch, and we'll both heat up this center bar.
Okay.
Then what's going to happen? It's going to get longer, right?
Yeah, it's going to expand.
Okay. Then with the gloves on, I'll tighten this to take up that slack.
All right.
Then we'll continue to do that, about 2-3 times until we get it nice and tight.
So while you heat it up, the slack is getting bigger.
Right.
Okay.
Now, have you ever used one of these torches?
No.
Well, they're very hot.
Okay.
You can push on this lever. Watch.
Oh, it heats up.
Okay. So then you heat it over here, heat the bar over here, and then when I get ready, I tell you, you move it off to the side.
Okay.
Okay? Okay?
Another quarter
Yeah,
turn.
another quarter turn.
Oops, I think mine went out.
Yours went out too?
It's getting pretty tight.
About 3/4 of a turn. Okay, now we've taken up all the slack. Pour water on the bar that we've been heating. And
All
what
right.
should happen?
Well, it'll get smaller.
Yeah, and what'll happen to this bar down here?
Well, I think it might break because
think
it's
so?
going to get
You
really
tried to
tight.
break, you remember how strong it was. Okay, pour the water.
Oops. There it goes.
Yeah. Good, this one fell in the water, so it won't be hot. There's half of it. There's the other half.
That's
So you
it, all
see
right.
how strong that molecular action is when you heat something and when you cool it down.
Can
It
even
broke
break a strong bar like this.
right in half.
All right, now let's go back to that question we did before. Which has more thermal energy? Well, now that you know a little bit more about thermal energy, do you want to change your original vote? Well, it might be quite a surprise to you, but the snow fort has more total thermal energy than the lit match. How is that possible? Why is that? Well, remember, thermal energy depends on the number of particles and the amount of energy in each. So you can imagine the particles in the snow fort are probably moving quite a bit slower than the particles in this lit match, but there are way more particles in the snow fort than there are particles in the lit match. One way you can think of it is, could this lit match melt this huge snow fort? No, I don't think so. Not going to be enough total thermal energy to do so. Definitely don't try this at home, kids. Not safe.
The liquid nitrogen, which is in here, will expand the bottle to the point where the bottle explodes because of pressure. This is not a combustion, like this is not a fiery explosion. This is an explosion due to pressure. Bottom of the can. I added water to the bottom of the can, which will actually help this whole thing happen. Any guesses why? What do you think?
The water is room temperature, and so it will
Right.
like speed up the heating.
The water will speed up the process of the liquid nitrogen boiling and boiling into a gas and expanding. So if we just stuck the liquid nitrogen in there with no other thermal mass, it would take quite a while for it to get enough pressure to blow up the bottle. But by giving it that water to speed it up, then it should take maybe 20 seconds or so. Well, the can does a great job of actually forcing most of the force of the explosion upward, just like a cannon might, and then that makes the bucket, which is sitting over the top, fly up. So, at this point, I would like you guys to get behind over there. Good timing. We counted exactly the right timing. That was so good.
2, 1.
I ran.
That was so cool.
A good analogy to this idea of the ice fort versus the match is think about maybe a garden hose versus a super soaker. Like the match is high pressure, it has a high temperature, it feels hot, and the garden hose is a much lower temperature, but there's a whole lot more particles of water that's coming out of the garden hose than there is coming out of the super soaker. So the super soaker, you might get a little bit wet, but the garden hose, you're going to get a lot wet. The super soaker hits with more pressure, but the hose is going to get you the most wet. Here's a clip that's kind of goes along with this pretty well. Fire hoses. Fire hoses come out with high pressure, but there's also a whole lot of water at the same time. Now, this is a firefighter training for what happens if the hose gets loose. Now, for this experiment, they took the couplings off of the hose because normally there's going to be a big metal piece of brass on each of these hoses, which is flying around that could hit you and actually severely injure you. So they took that up for this test. Pretty fun to watch though. Check it out. All right, well, thanks for joining us. This is the end of part 1. We'll carry on with thermal energy and temperature in our next edition. See ya!